Okay, let's talk about rotational dynamics and moment of inertia, also known as rotational inertia. Okay, let's quickly review a little bit about angular velocity, angular acceleration. So say this is the angular theta right here, and eventually we'll have a rotation going that way. So we have a radius of this is not necessarily a circle. What we are thinking is here's point mass, and then it's rotating from about the center, okay? And then this arc length, we'll call it S. So do we all remember arc length formula? S is equal to R theta then? So far, so good. Now, what happens if we take a derivative on both sides? So here's S, and then here's R theta, and we're taking a derivative with respect to t. And assuming R is constant, which doesn't necessarily have to be constant, but at this level, it is pretty much constant, isn't it? Then this gives you the velocity, correct? Which we call linear velocity, which happens to be the velocity of this thing moving. It's linear speed, more like, because velocity includes the direction, so it's a linear speed. Good? And this is what we call angular velocity, omega. Good? So we are familiar with definition of angular velocity now. We define angular velocity as d theta dt, the rate of change of this angle in rotation, how fast this is rotating. Okay, now what happens if we take a derivative on both sides again? R and omega, and take a derivative here with respect to time. Then on the left-hand side is what we call acceleration, correct? Linear acceleration, how fast this thing speeds up or slow down in a circular motion. And right-hand side is what we call angular acceleration, alpha. And that's another definition. Alpha is defined by the omega dt, which means it's a second derivative of theta. So far, so good. Okay, so this is pretty good information to have on the side. Okay, that didn't work out too well now, did it? Let's do that. Okay. Then, do you remember this kinematics equation? The distance or position happens to be S naught plus V naught t plus 1/2 AT squared. Good. Now the S over here is equal to R theta, isn't it? So this is R, and then theta, which is function of t, because theta is changing at the moment, correct? And then S, this is still R of theta original then A, and plus V. Where is V? V is R omega A. So we have R omega original plus 1/2 A. A happens to be R alpha. Right? I believe I forgot T over there. Good. Now we can divide both sides by R. So we have this theta, which is theta original plus omega naught plus 1/2 alpha t squared. This thing looks exactly like this now, doesn't it? Which tells you the same kinematics equation applies, right? Instead of acceleration and velocity, we use angular acceleration and angular velocity, but that's it. Okay? So far, so good? Okay, now we'll get to this, but I want to do a little quick calculation, which is, say, what is torque from previous section in statics? Torque we defined as R cross F, right? which is really, let's say in our case, we have, this is R vector, good? And then let's say whatever the torque we are applying this force at a perpendicular angle for our purpose now, because this is a rigid body rotation is what this chapter is all about, okay? Then this magnitude of tau happens to be R F sine theta, isn't it? But in our case, the sine theta, theta being 90 degrees, so this is 1, so far so good. Okay, then this is R, and F is equal to MA, eh? Hopefully you still remember that much. What was A again from up there? R alpha. So what we have is M R square alpha. Tau is equal to mr square alpha is one little thing that we get. Okay? Okay. You just started angular momentum, eh? Which is defined by, wait, where am I putting that kind of vector symbol? R cross linear momentum, eh? So if you just look at the magnitude, this is R, and then this is MB. And then, of course, there's the sine theta. But for our purpose, once again, this is 1, eh? This angle is perpendicular. Okay. Then what that tells you is R, M, and what was the from up here? R omega, eh? So we substitute R omega here. Push this thing down a little bit. So our L is equal to mr squared omega. Okay, let's think about kinetic energy. Kinetic energy, of course, is 1/2 mv squared. Eh? If you have a point mass rotating with a radius r, you know what I'm saying? Okay, but v once again is r omega squared. Eh? Okay, so this kinetic energy here is 1/2. Here we go again, mr squared omega. Let's just, omega squared. Let's just think about this a little bit, okay? If we let I to be mr squared, and you see where this is going, right? And then this thingy becomes tau is equal to I alpha. This thingy becomes L, angular momentum is I omega, and you've seen this today probably. And then this, your K is equal to 1/2 I omega squared. Now, I'm not sure about you, but does this thing look awfully like F is equal to MA? And this thing awfully looks like P is equal to MV. And this thing looks like K is equal to 1/2 MV squared now, doesn't it? It really resembles all of these things that we've been doing in kinematics. You know what I'm saying? So same techniques and laws apply to all of it. Only thing is this mr squared, right? This mr squared is what we call the moment of inertia or rotational inertia. So that's great, but only assumption that we have here is this is a point mass, the distance r away from it, right? Okay, so what happens if we have a bunch of these masses? Have you done this kind of problem in the class? Then I'm going to skip it and go into integral. No? Okay, let's do this. So situation, now this moment of inertia or rotational inertia matters where your rotational axis is, okay? So our situation is we have 4 point masses, negligible size, and then the blue masses have capital M as mass, and then is it yellow? from whatever, orange, weird color, has lowercase m, right? And then our rotational axis is this way. Good. So we'll calculate the moment of inertia or rotational inertia of all of this whole body. Okay, and these rods that connects them are negligible mass. So only thing that contribute to our rotational inertia are these masses. Good. Okay. So the way you think is how much torque does it take to rotate this thingy? You see, these two masses really don't contribute much because it's on the top of the rotational axis. It's only these two that requires a torque. Good. So A, what you want is, we'll just calculate I1 happens to be 1/2 capital M and then A square, R squared. This is A. You know what I'm saying? Did you get that? You look puzzled. MR 1/2 MA squared. Good. Okay. And then I2 is also MA squared. Let's say this is 1 and this is 2. What about I3? That's lowercase m and then 0 squared, isn't it? And then what about I4? Well, this is 3 and this is 4. So that is also lowercase m and 0 squared. So the total moment of, why do moment of inertias or rotational inertias add? That's got to be a question that you had. Is there any reason for this to add? We'll think like this. Amount of torque that is required to rotate that thingy. So this is T1, tau 1 is I1 alpha, isn't it? In this case is MA squared alpha. Whatever, this is the angular acceleration that is required to rotate this thingy. And then tau 2 is likewise MA squared alpha. And tau 3 is 0. And tau 4 is equal to 0, correct? Then as you can see, the total torque is just, you just add tau 1 plus tau 2 plus tau 3 plus tau 4, right? Does that seem natural to you? Now, if you add these things, alpha is a common factor, so you have I1 plus I2 plus I3 plus I4 alpha, isn't it? You see why they have to add? So the total moment of inertia is I1, in this case, I1 plus I2. So we have 2 times MA squared. Good? Say yes. Okay, we'll consider case B then. Case B is, now we are rotating about this pivot point. Okay? So these two have radius of A, and these two have radius of B, but this B part also contribute to moment of inertia. Good? So we'll just call this thing 1, 2, 3, 4, as we did before. So part B, I1 is equal to MA squared like before. And then that is also equal to I2. And I3 is equal to lowercase m and B squared. Eh? And that is also equal to I4, correct? So in this case, the total moment of inertia is equal to 2 of MA squared plus 2 of lowercase m B squared. Do you understand why the moment of inertia add naturally? And so it depends on a couple of things. It only depends on the geometry, because acceleration and angular velocity does not enter this equation. right? Number two, but it does depend on the rotational axis. Depending on which axis you rotate from, exact same objects have different moment of inertia. Okay, so this is a table that you have to memorize, buddy. Right? This, you don't have to memorize this, right? So this one, do you have to memorize this? Nay, this one definitely. Then this one, this one, this one, and this one, not this. I will integrate and calculate all of these. Well, some of it, and I will leave some of it as exercise. Let's do this one first, okay? So the way we think is like this. We have a rod. So this is a whole idea is one-dimensional object. Well, that didn't work out. Let's do that again. Okay, we have a rod. And then this is where we're going to put x-axis here. So x is equal to 0 here. And at this point, x is equal to L. So the length of the rod is L. You get it? Okay, we'll take this tiny little infinitesimal mass. Because the rod, anything is made of, all of these molecules add up. And then each molecule will have a moment of inertia of mr squared. You get it? Okay, so if we rotate this around, what would be our moment of inertia? We'll call that dm, okay? You will call that di. Okay, and that has to be the distance, this radius, right, which is what we call x, and then m dm r squared or x squared. You get that idea? And the mass of this thing, of course, is dm. Then what is dm? Let's introduce the concept of length density. I think we have done that before. Length density is good. It's more convenient to just have that instead of carrying that thing around. So do you see that dm has to be dx times lambda? And then we'll put x squared, let's write it like this. So we have lambda and then x squared and then dx. That makes sense to you? For those of you who are hesitating, m is equal to lambda times L, right? L length, so derivative on both sides, or take differential, so this is dm, and this is lambda, and this is, instead of dl, we're calling dx. So that is more natural for us to integrate. You get it? Okay, so all you have to do is integrate this. So your moment of inertia here is from 0 to L lambda x squared dx. Good? And that gives you lambda over 3 x cubed from 0 to L. And that gives you, I'm going to push this thing down a little bit. Okay. That gives you lambda over 3 L cubed now, right? Remember what lambda is. Lambda is m over L. So we substitute that in. So we have 1/3 lambda, and then we put m over L, and then L cubed. And then L's cancel, so you have, yes. Sorry. Oh, lambda is that. Good. So L's cancel, so we have 1/3 ml squared, as you memorized. What that means is all of these little molecules, since moment of inertias add naturally, we'll think of this as infinitesimal size molecules, and all of them, we'll just add them up. So it becomes this naturally. Good? Next one that's important was hollow sphere. Let's just take, even if we call these things, let's say, somewhere around di, where dm, but then rotational radius is all r. Good. Do you see then this I has to be just mr squared? because they all have exact same radius. So even if we add it, nothing is varying. There's no variable, so everything will just give you exactly that. So we'll just leave that one. Now, then the next important is this, and actually this is the most significant one in physics because there are so many pulleys and wheels, right? Okay, so cylinder, pulleys and wheels are all cylinders. So we'll do this one, okay? In order to do this one, what we have to do is each of this will create inside. Let's see how good my skills are with this thingy. Zoom in. My finger. Do you remember cylindrical shell technique? Let me draw another one. I failed. That's okay because I can do this. So inside, there is a shell. You know what I'm saying? That is my DI, or DM. Good? Now I have to zoom out, and my finger does not want to respond to this computer. I cannot zoom out. Oh, okay, that worked too well. Okay. So we're going to call this moment of inertia due to this thin shell di. And it's got to be exactly the same as this case now, isn't it? So whatever that mass of this thing, dm, times that radius, we'll call it r. Good. So when I say r is this radius of the, can you see it? That little cylindrical shell that we drew, where capital R is the radius of the cylinder. Okay? Alrighty. Well then, we'll have to figure this out. Do you remember from chapter 7 what this, well, dm is, of course. Let's define the density, which is mass divided by volume in this case, eh? So what's the volume of this cylinder? Is it r squared, pi r squared times h being this? And then are you getting a little concerned that we are bringing another variable into our equation? Just hold on right there, okay? Okay, then let's think about what dm is. dm has to be our density times, we'll just put r squared here, and then it has to be dv, eh? So far with me? We'll draw this dv out. If I cut this thing and spread it open, it's going to look like this. Little bit review of cylindrical shell. So this is h. It used to be y in our class, but this is constant h. And this is the circumference of this cylinder, which is 2 pi r. And then the thickness right here is dr, isn't it? So this dv, I'll write it here, is 2 pi h r dr. Good? Substitute that here, so our di becomes 2 pi rho h, all constant, and then r cubed dr. Good? Okay. Then our I is from 0 to capital R, and then we have 2 pi rho h constant, and then r cubed dr. Good? Is it okay if I use dr here instead of dx? I mean, just x-axis, kind of same thing, but I'm just trying to be a little more general here. Then all we have to do is integrate. So this thing becomes pi rho h r to the fourth power, therefore 1/4, cancel that, and 1/2. And then from 0 to capital R, right? Okay, so 1/2 pi, what was rho? That, substitute that in, m over pi r squared h, which cancels this h, you see that? And then we have r to the fourth power, r's cancel, and this pi's cancel. So what we have is 1/2 m r squared, as you learned in the class. How about that? Okay. Lastly, this one. This one is something, okay? So in order to do this one, we'll create a little bit of a picture. Let me draw this, and we're going to have axis running in the middle. This thing never works out exactly the way I want it. Okay, there. Better. Okay. We'll have circle. Okay? Equation of the circle x squared plus y squared is equal to capital R squared. Okay? We're going to draw rectangle right here. And then we're going to rotate this. Okay, that's my DI. Pretty much the same way as before. So first of it, okay, then, so we'll call that DI. DI is still the density of this thing times dm times r squared, isn't it? But density, well, density is not there. dm times r squared, eh? Okay, so let's get the density here. Let's define our rho as mass divided by our volume. What's the volume of sphere without integrating? That, we're going to substitute that later, or if you want to simplify now, 3m over 4 pi r cubed. Okay? So dm has to be density times dv, correct? So let's put dv here. Okay? Now, our dv, we have to figure out our dv. So let's just do dv. Let's do a quick review. Now, here's dv, which is, once again, the circumference, which is 2 pi x now. X is from here to here, and from here to here is y, isn't it? So do you see it's a 2 pi x times 2y times dx, dx being the thickness of the slab. Good. I don't have to throw the rectangles again, right? Okay, then, which we have 2 pi x, well, 4 pi x, and then what's y? My y. Y is this thing. So square root of, you see why I wanted to do this separately. That's my dv. Okay, so far so good? Now, we substitute it here, okay? Now I have x here, so let's convert these things back to x, because our rotational radius is at the moment x, the way I drew it in two-dimensional, okay? Do you see the situation we are in? X cubed, because we have x here and we have x squared there, and then square root of r squared minus x squared dx. How many of you know how to integrate that thing? Good. One. Let's do it, right? Okay. So that's the setup, and rest of it is integration, showing our integrity. And I'm going to need a lot of space, okay? So my I happens to be integral of, from 0 to capital R again, right? Of 4 pi rho x cubed square root of r squared minus x squared dx. Oh, by the way, for your information, if you do this in 3 multivariable calculus, triple integral in a spherical coordinate, then it's so much easier. But I think we have enough integrity. Here's the trick. We do this with a u sub. Well, if that's u, that's not the u, right? Integration by part. Here's a trick. Let u square to be r squared minus x squared. What I'm doing here is u is equal to all of this, including the square root. Then I need x, right? So x squared, of course, is r squared minus u squared. So far, so good. I need dx. So implicit derivative 2x dx is equal to r dice, so 2u du. So far, so good. So my dx happens to be negative u over x du. Okay, ready for substitution now? Taking 4 pi rho outside, and then I'll leave this x cubed here for now. This whole thing is u, isn't it? And then I substitute dx. So we have negative u over x du. With me? Now we have to change the limits of integration. So when x is equal to 0, my u is equal to r squared. When x is equal to capital R, my u becomes 0. Good. Okay, let's see what we got. Taking the negative sign out, so we have negative 4 pi rho, and then x cancels. So I have x squared u squared du. With me so far? Are you with me so far? Okay, then, what is x squared? X squared is this. Substitute that in. So what we are going to have is r squared x squared minus u to the fourth power du. With me? Yes. Okay, when we do the u sub, we'll start with when x is equal to 0, right? So we substitute that here, and then, oh, you mean this thing has to be r, is what you're asking, right?
In the last thing, it's r squared u squared, not r squared x squared. On the very bottom.
Here?
Yeah.
I substituted that thingy here. So I distribute u squared. Oh, this is u squared. Nice catch, both of you. Good. So far, so good now? Okay. Now we can integrate. Wasn't that a nice trick? So we integrate. So that's negative 4 pi. You want to switch this to and get rid of negative sign now or later? Now? Okay, make that positive, and then have 0 to r then, eh? Because when you switch the limits of integration, you just get the opposite. R squared u squared minus u to the fourth du. Good. Integrating now, so we have 4 pi rho, and this becomes u cubed, therefore 1/30, minus u to the fifth power, therefore 1/5. That 5 does not look good. And then from 0 to r. Good. Okay. Now substitute. So we have 4 pi rho. And if you plug in R here, you get R to the fifth power. And then R here. Okay, time to add fractions. Somebody tell me how those fractions add while I substitute rho. Remember, rho is way, way, way up there, 3m over 4 pi r cubed. 3m over 4 pi r cubed. Are you done? What do you have? 2/5 r to the fifth power. Do you see it yet? 2/15. Do you see it yet? Okay, let's start canceling. 4 pi cancels 4 pi. This thingy cancels that and leaves you 2. This thingy cancels, right? So as you see on the table, 2/5 mr squared. That's just amazing, isn't it? So the current theme is still mr squared, but at what fraction? At most, when you have all of the masses concentrated at the outer edge of the possible rotation, then it's 1 mr squared. You get it? Anytime you move this mass inside, if you concentrate everything on that axis, you get 0 because of that r squared, individual r squared of the molecule. And if you're somewhere in between, then it's got to be less than 1. So it's at what fraction of mr squared? So mr squared is the maximum moment of inertia you can get. Good? Okay, we'll take a couple of test-worthy questions. Oh, this thing shows up on AP all the time. You are familiar with the pulley system, right? Except it used to be, all the pulleys used to be weightless. Now this pulley has a weight. And we say this radius of the pulley is r. And then, of course, I threw in a little friction, right? Find the acceleration of the whole system. Yikes, right? Okay, we'll look at system 1. Just throw it with the red. System 1, M1, right? So I don't have to tell you this force is equal to M1G sine theta. And then we have tension pulling it back, right? But then this tension here and this tension here used to be exactly the same. Now we have two different tensions. Like, why is that? Yeah.
Because the pulley itself also has.
Pulley itself has a mass, right? So something has to rotate the pulley. And what's rotating the pulley is the difference of two tensions. Tensions are forces. If they are same, pulley is not rotating, then we don't have an acceleration. You get it? So if you exaggerate the picture, then you imagine this is a gigantic stone mill. And then you hang a mass on one side and don't even hang anything. That itself has a tension and the other side has nothing. You see the difference of tensions? So these two are not the same thing. So we have to call this T1. And then a little bit of friction, right? That is, of course, mu m1g cosine theta is what we got. Good? So the equation is m1g sine theta minus T1 minus mu m1g cosine theta is equal to 0. Good? Oh no, is it? No, is equal. What I'm saying? Is equal to m1a. Good? Because net force is equal to ma. Okay, I'm going to call that equation 1. Okay, let's look at the situation on the second block, m2. This one is easy. So downward, you have m2g. I'm going to throw that arrow smaller. Right? And then, actually bigger. And then upward, there's T2. Okay. Wait a minute. Let's hold. Let's back up right there. We have to decide which way the motion is. How do you know which way the motion is? Without the friction, it doesn't matter to us. Because if you get the negative number, it's fine. How do you decide which way the motion is it going to move? So this M1, is it sliding to the left or upward to the right? Is this M2 moving down or moving up? Because direction of the friction depends on that. Yes?
I guess that's if M2 is bigger or smaller than M1.
Not necessarily. M1G times sine theta versus M2G is how you figure this out. Because remember, this force down the line is M2 mg sine theta, correct? That is fighting this M2G, right? And usually they give you the mass and the angle so you can decide which way it is. For the sake of this example, which way do you want it to go? Because the direction of this sign of this friction changes, depends on that. Do you want to go with, do you want M1 to slide down or slide up the way it's looking? Let's make it go up because most questions actually make it go up, right? So what I'm going to do here is I'm going to reverse the direction of the friction. I'm going to make this thing smaller, this thing a little bigger. So this is a realistic situation. And then here's a friction. Get it? Good. And then which direction is positive direction then? How do you decide positive direction in this situation? This is positive direction. You know what I'm saying? The direction of the motion is always positive. It does not have to be straight. So I have to change all of this then. Okay? So what I'm going to say here is T1 minus M1G sine theta minus mu M1G cosine theta is equal to M1A in that positive direction. Good? Okay, from here, now then this is positive direction and this is negative direction, right? So what we have here is M2G minus T2 is equal to M2A. Are we good? Let's review what we have. How many variables, how many unknowns do we have? We don't know A. We don't know T1. We don't know T2. We have a problem. We are one equation short. This is a systems of equation, but we don't have one equation. That comes from the pulley torque equation. I'm going to zoom in there and draw this thing out. So we have this pulley, and then we have this direction torque, which is T2, and we have that direction T1, and at the moment T2 is greater than T1, and that rotates the pulley, and the radius of the pulley is R, and mass of this is M3. Good? Do you remember the net torque is equal to I alpha? Right? Okay, what is net torque? Torque rotating this way and torque rotating that way, but this is a positive direction and that's a negative direction for us. So net torque is T2 and then times R, right? R times R cross F is our torque, minus R and T1, correct? Tell me what the moment of inertia of a pulley is. We just integrated 1/2 m r square, right? And then alpha. You with me? Okay, so divide both sides by r. So we have T2 minus T1 is equal to 1/2 m r alpha. Tell me what r alpha is. A. Now we copy this and paste it up there. You get it? So we have T2 minus T1 is equal to M3. Sorry, M3. Our pulley is M3. Now we have this beautiful systems of equation. Have you ever solved anything like this before? It's 3 by 3 systems of equation, but this is ugly, right? It's not that ugly, it's actually beautiful. You just add them up vertically and let's see what happens. Do you see this T1 cancels T1 here? This T2 cancels that T2. Oh my God, this is a beautiful elimination. Both of the variables cancel out, and then you have M2G minus M1G sine theta minus mu M1G cosine theta is equal to, and the right hand side, M1 plus M2 plus M3 common factor A. You with me? So therefore, finally, our acceleration of the system is, you want a common factor G? Yeah, sure. G, M2 minus M1 sine theta minus mu M1 cosine theta, all divided by M1 plus M2 plus, I dropped 1/2 here, right? Because we had half down here. Good. 1/2 of M3. Huh. These things show up on AP exam all the time, or variation of this type of problems. Good. Finally, we'll do a roller coaster and then call it a day. Say we, instead of regular block on a frictionless plane, we actually have solid sphere, right? And we are going to roll it, and then it's going to make the loop. Now, this original height has to be high enough in order to make the loop, otherwise it will drop. So the question is, what is the minimum in order to make the loop? Good? Oh boy, this is complicated, right? Okay, so original potential energy, right? Potential energy U has to be mgh, and that's it. Okay, that's the original. Now we consider when our solid sphere, the bearing, is right there. Okay, negligible r is slightly less than r, but let's call it r. Then the energy, we'll just say energy initial. Energy final is kinetic energy plus potential energy, isn't it? What is the kinetic energy then? 1/2 mv squared plus space plus mg, the height, 2r. That makes sense to you? Then what is that space doing right there? I'm not sure if you remember, but at the beginning of this lesson, rotational kinetic energy, right? What was it? Remind me again? 1/2? It looks, right, it looks very much like this, I omega squared. And there, if this thing is just rotating alone, it has this kind of kinetic energy. If it's moving alone, it has that. Sliding alone, it has that much kinetic energy. If it's rolling, it has combination of the two. For that reason, it moves a lot slower than sliding block, because see all of this energy, Before, this didn't happen, so it was distributing between the two. Now you have to distribute between the three. So it's going to move a lot slower if this thing goes without slipping. Yikes, we're going to equate this too, huh? Well, we'll clean this up a little bit. What is the moment of inertia of solid sphere? We integrated it, do you remember? 2/5, right? M, same M, and then R squared, correct? And then omega squared plus 2 mgr. With me? Okay. We have 1/2 mv squared plus 1/5 then m, and then we have r squared omega squared. What is r omega? At the very beginning, I really don't want to scroll back up. That is v, right? V is equal to r omega, right? So this is v squared plus 2 mgr. Do you see these two are like terms now? Fraction addition, tell me what it is. 7/10 is correct. Now we equate the two. I guess we'll not get to parallel axis theorem, or we could if you want to. Okay, so if we equate I initial to E initial to E final, what we have is mgh on the left-hand side, 7/10 mv squared plus 2 mgr. Good? Do you see m's cancel out? So it's still independent of mass. Okay? And then what we have is, let's just write it like this. M's cancel out, and we have GH minus 2GR, or G, yeah, is equal to 7/10 V squared, eh? Okay, remember we want to know the relationship between H and G, okay? Now, we'll think about the normal force on the track now, okay? So let's say this is the top portion of that track, and our sphere is at the top. This, good? Now, let's draw the force diagram here. We, of course, have mg. And then we also have normal force here, right? Downward, because if your hand has to be up here to press this thing down, if this is your hand, and then when this thing rolls, you have to press it down, then your hand has to push it down. Gravity will help you, but still, otherwise it'll go up, right? But we want the minimum height, right? We want this thing to barely make it, correct? So we want to find out what that is. And if we don't have enough velocity, where the normal force is 0, so gravity alone will be the centripetal force. You get it? Otherwise, if it goes slower than that, then it's going to just fall, and then we are not going to make the loop, right? So what is the situation then is our centripetal force has to be mg then. That makes sense to you? Okay, now centripetal force, of course, is fictitious force. Some real force is acting as a centripetal force, correct? So centripetal force is mv squared over r is equal to mg. Good? That means v squared, m's cancel, is equal to gr. Good? Good, good, good. Now we substitute it here. I regret moving this thing over to the left. Why did I do that, right? I'm going to leave it. Because now I realize, right? So, plus we have 2gr. Good? And then we take this v and substitute it right here. So what we have here now is gh is equal to 7/10, and then v squared is equal to gr. Right? So yes. Plus 2gr. Wow, we can divide both by g. So it's independent of the planet. In any planet, it has exactly the same relationship. Isn't this something? Let's just write it as 2.7r. How about that? Right, so this original height has to be 2.7 times the radius of this track. You know what I'm saying? This is 2, so 0.7 about here. Has to be the minimum, not quite 3. Of course, if you go to amusement park, they make it way higher than 3 times the radius just to make it safe and the friction and all that. But if in ideal situation, it could be just 2.7 times the radius of the loop and it'll make it safely. Huh, okay. You want to finish this off? Parallel axis theorem, have you dealt with this before? So parallel axis theorem tells you where the pivot point is, moment of inertia of this. Let's say this is a disk, kind of like the bob of a grandfather clock. Let's say we have that. So moment of inertia of this thingy, cylinder, right, is equal to 1/2. What do you want to call? Let's give this guy mass m and this guy mass lowercase m, right? M r squared, and then radius of this thing, let's say, is r. Good. From its own center of mass, or center, whatever, that we calculated, right? Okay. And then, what is the moment of inertia of this thingy? Say, moment of inertia of a, what is it, rod, is 1/3 ml square, where L is this length. My pen is not working. L is the length of the entire stick. Good? Now, parallel axis theorem states the total moment of inertia from this point, which is the pivot point, has to be, well, this one is easy, just that one, right? This one, total moment of inertia, is this plus mr squared, and our r happens to be from here to here. Why? Why? There are two ways of justifying this. One way is to integrate, which I really don't want to do. Second way is actually use the torque idea, okay? Let's just calculate the torque that is required to swing this thing back and forth, okay? So the torque has to be, of course, I alpha, right? So we want to calculate the amount of torque to accelerate this thing with the angular acceleration alpha, whatever that alpha might be, okay? So let's say torque of the rod is easy, right? This one is 1/3 ml squared alpha. Okay, we'll let that sit there. Now we need the torque of the cylinder. Okay? Now, what we have to do is, let's consider this is a point mass at the moment, which is not, but let's just think about it. If it's a point mass, it's easier to swing it instead of actual rigid body. Because rigid body, you have to not only swing it, but you have to rotate it as well. You know what I'm saying? So the amount of torque it takes to swing this thing has to be the moment of inertia, treating this as a point mass, which is m r squared. Now our r here is from here to here. which is little r plus L. That makes sense to you? So mr squared is times alpha. Now, but we also have to provide additional torque to make this thing rotate. Correct? So that happens to be plus mr squared, right? Its own I alpha. That makes sense to you? So the total torque is common factor alpha, mr squared plus 1/2 m lowercase r squared. All right? So far with me? And then this happens to be the moment of inertia, which is away, not from its center of mass, but distance r away from it. You know what I'm saying? So this is the moment of inertia of that thingy. So moment of inertia that is some distance r away is always the moment of inertia from its center of the m r squared, treating this thing as a point mass, plus moment of inertia of its from center of mass, which is the second one. You just add this term. Oh, that makes perfect sense, huh? Questions? You're not inspiring too much confidence right now, so did I go too fast? And then total moment of inertia is, of course, all of this plus that. Good, and then you substitute this thing in. So just grand finale, the total moment of inertia, moment of inertia is equal to 1/3 ml squared plus this thingy, m, and r, remember in our case is this, plus 1/2 mr squared. It's the total moment of inertia. Because we are using this relationship, torque is equal to I alpha. Good. So this is known as parallel axis theorem. Whenever you are rotating stuff not from its own center of mass, because all of our table gives you the moment of inertia from the center of mass. So if you want to rotate it from some distance far away, then you just add this additional term because it takes that much more torque to swing this thing around. Good. Questions? Alrighty, we'll call it a day then.